CO2 takes different forms in acidic and alkaline solutions. This super-fast new carbon removal technique takes advantage of that by switching acidity on and off using light. Capturing carbon dioxide emissions will be critical to meet climate goals according to the United Nations, and efforts are underway around the world to do this at large scale. But the technology remains expensive and energy-intensive. Now, researchers present a way to use light and special light-triggered molecules to pull carbon dioxide from a mixture. The method, reported in the journal Chemistry of Materials, could be powered by the sun, cutting the energy needed to capture the greenhouse gas. The scientific community has been working for decades on technologies to capture CO2. Today, 30 commercial carbon capture projects are operating around the world with 11 more under construction. These projects capture emissions at power plants or industrial facilities using liquid or solid materials that soak up CO2. But the materials can be costly, and to reuse them, they have to be heated to strip the CO2. The gas can then be stored or used for making chemicals. Maria Lukatskaya, a professor of electrochemical energy systems at ETH Zurich, and her colleagues developed a new carbon removal technique that relies on the fact that CO2 takes on different forms in an acidic versus an alkaline solution. In acidic liquids, it stays in the form of CO2, but in alkaline solutions, it reacts to form carbonic acid salts or carbonates. Recommended reading: What's a better investment, renewables or carbon capture? This chemical reaction is reversible, and it can be switched by reversing the acidity of the liquid. The researchers found a way to switch that acidity using light. They added special light-activated molecules called photoacids that make the liquid acidic when exposed to light. When it is dark, they return to their original state and make the liquid alkaline. So to capture CO2 from a gas mixture, the team first passes the mixture through the photoacid-containing liquid in the dark. The alkaline solution triggers the CO2 to form carbonates. Once there are sufficient carbonates in the liquid, the researchers irradiate it with light. This makes the solution acidic, and the carbonates turn to CO2, which bubbles out of the liquid and can be collected. Then, the researchers start the cycle over again. The process should work with sunlight, the researchers say, and it takes seconds to minutes for the acidity to be reversed, so the cycle is fast compared to heat-driven approaches. Right now, the photoacids decompose in the liquid after about a month, so the team is working on making the molecules more stable and further optimizing the method.